Hey everyone, thank you so much for watching this paper summary video of HNSW-FINGER. FINGER is short for Fast Inference for Graph-Based Approximate Nearest Neighbor Search. The authors present a super clever technique that extends the HNSW algorithm perfectly by approximating distance calculations. So we're going to approximate these distance calculations by computing a lot of values offline using these cool algorithms like singular value decomposition, all sorts of details that we'll explore in this paper summary video. But to give more of a TLDR, HNSW-FINGER trades off additional memory for faster vector search. So when using this algorithm, that's the trade-off basically. So we'll get into exactly how much memory and exactly how much of a speed up you get. In terms of the evaluation, you're especially going to see the benefit of HNSW-FINGER when you're dealing with higher dimensional vectors. So they find the biggest improvement on just 960 dimensional vectors, but say just at the time of recording this, the OpenAI ADA2 embeddings are super commonly used and they are 1500 dimensional vectors. So you can expect a huge speed up on using higher dimensional vectors like that with an algorithm like this, and all that will be evident as we step into the math. So I had so much fun reading this paper, and I hope this video helps you, understand the math as well. It really helped my intuition on approximate nearest neighbor search as we look into the like the HNSW stop condition and all this cool stuff. So let's dive into it. Thanks so much for watching. Okay, so here's a quick overview of the algorithm in 2 minutes, just in case you want to get the high-level concept behind it. So the core value out of vector databases is approximate nearest neighbor search. We take a query, we turn it into a vector, and we want to find the most similar vector to our query in our database of vectorized documents. We don't want to have to compare the distance between our query and every single vector in our database, so we build up these data structures to facilitate approximate nearest neighbor search. So shown on the left is the HNSW hierarchical proximity graph to route these distance calculations such that instead of, say, we have a billion vectors in our database, instead of doing a billion distance calculations, we do, say, 10,000 or so, or however many. But so that's the core idea, is we build up these data structures. So within HNSW, we have the search layer algorithm for how we're going to traverse the graph. And we have this upper bound between the distance of the candidate and then the neighbor that we're exploring. And so we use those distances for how we append it into the queue or terminate the search. So the authors find that over 80% of these distances here, when we're exploring these neighbors, towards the mid phase of the search, they usually don't contribute anything to the actual end result, so we can get away with approximating these distances. So the key insight for how to approximate these distances is we're going to project the query and the neighboring node onto the center node. So again, the way that HNSW search works is we find some center node, like say this blue node shown in my mouse, and you're exploring the neighbors of that blue node. So this blue node is the center node C. So we project the query onto that center node as well as its neighbors. Now the cool thing is that we can then compute the projection of the neighbors onto the center node offline and store these offline, and then we just look it up and quickly calculate the distance. So that's done by decomposing L2 distance between the query and the neighbor into the separating it into the projected and residual components. So this is the key detail that we'll be exploring in this paper summary video, is understanding how each of these four terms are computed. This last one, the the angle between the residual components, that's the key meat behind it. But you compute these, most of it is stored offline, and we'll get into the memory overhead, but this is the key behind how it works. So there's also this clever technique of using a distribution matching, where you look at the the distribution of the angles between the real data, and then once you have the low rank projection, what the angle then becomes, and doing this kind of normalization thing. It's a super common thing to see in deep learning, so I think it's just cool to see this in general. So I maybe should mention that we measure this angle of the distances by with the data distribution. So we have the SVD, a low rank projection, by looking at the actual residuals in the distances. All this will be clear from the paper summary video, but just to give an overview, we use the data distribution to help with this approximation. So then finally, with the results, I think looking at this GIST 960 is the most interesting thing. You see a huge benefit in queries per second at different recall levels compared to just baseline implementations of HNSW. The benefit being not as big on lower dimensional vectors, 96, 100, 128, but these higher dimensional vectors, I don't really know too much about like the information retrieval benchmarks and how those react to higher dimensional vectors generally, but as I mentioned in the beginning of the video, the OpenAI ADA2 embeddings are 1536, so it seems that that would benefit from this enormously. So let's dive into the details further. This video will explain the technical details behind the HNSW-FINGER algorithm. To give a quick overview of the presentation, we're going to start off by exploring the HNSW Search algorithm and particularly the stop condition and how we're exploring the neighbors to our current center node and comparing that with the upper bound, which is the furthest distance in our working queue so far. So the key insight from that is that over 80% of these distance calculations don't contribute anything to the final search result, and thus we can get away with approximating these distances. So that's where the devil is in the details, is in looking at how exactly we approximate these distances. So they first show the decomposition of the L2 distance into the projected and residual components. We'll get into how exactly we're going to compute our basis by having the SVD of the residuals as we build a matrix of all of the edges in our search graph, and then low rank approximate that, and then use that to project the vectors into the space, and then have the projected and residual components. And so there's a lot of details behind this, but I think it's so interesting once you finally wrap your head around it. And I think in addition to understanding just what values need to be pre-computed, you see the memory overhead as well, and which is the third point, is understanding the details behind the memory overhead that this creates, and I think that further just helps you understand the algorithm. So then we'll get into this distribution matching technique. You use the data distribution in that SVD decomposition to project the vectors, so it's pretty interesting to then align the real angles with the projected angles by using this kind of distribution matching technique, which is a super common thing to do in machine learning, and so it's really interesting to see it in this algorithm as well. So then we'll get into the results. I think the most interesting takeaway, as mentioned in the beginning, is that you get the best performance from higher dimensional vectors, which makes a lot of sense as we look at the math, because obviously you're not having to do all of the distances on a 960 dimensional vector, and so it makes a lot of sense for why that is the one that performs the best. But I think it's just interesting to see. Then we'll talk about some future directions, particularly maybe comparing this with product quantization to understand the difference between the two algorithms, as well as just maybe what we can do further with this kind of distribution of the data to speed up distances. Okay, so once we've built up an HNSW proximity graph, we're going to be exploring it by using the algorithm shown here, the search layer algorithm. So search layer takes as input the query, the entry points from the previous layer, say layer 2 down to layer 1 or layer 1 down to layer 0. We start with these entry points that come from searching the top layer, and that's where the hierarchy of the approximate nearest neighbor search comes into this. So then we have the EF. EF is one of the hyperparameters to be looking at as you're, say, like tuning Weaviate and looking at, EF. It's the size of the queue as you're searching. So, if you have a super big queue, then you're going to have a longer search, and so on. So, and then you have the layer number that you're searching through, particularly because usually you'll store the proximity graph, as like a dictionary where you index it with the layer number and things like this. So the output is going to be the EF closest neighbors to the query. So we initialize the visited set, the candidates, and the dynamic list of found nearest neighbors, the CW, the V set. So then while we still have elements in the candidates, we're going to pop the nearest element from C to Q from that candidate queue. Then we're going to peek at the furthest element from W to Q. Then this is going to be the terminate the search condition. If the distance of that nearest neighbor is greater than the furthest element, then that means that we've evaluated all the reasonable candidates to be searching through. So now we're stepping into probably the most important thing to be looking at with particularly this paper is, so for each E in the neighborhood of C, so we've popped up C, it's the nearest element to our query, and now we're going to be exploring the neighborhood of C. So say this red point is our query, and what would be a good example? Let's say, so this is our query, this red point, and then we bring this blue point with us into the layer 1. So now we're exploring the nearest neighbors to the red point, which this is our query again. So now this node is the closest node to this one. So, this becomes our new furthest element, and this ends up being the entry point as we come here. Or I guess the green one is supposed to be our query, but anyway, so I think you get the idea. The green one is supposed to be the query in the top layer where this is the nearest neighbor on layer 2, and then this is the nearest neighbor on layer 1, and then that takes us into layer 0 or so on. Anyway, so that's basically the idea. I don't know if that picture is super clear, but basically, so once we're there, we're going to add this neighbor to our visited set, and then we're going to get that furthest element from W to Q, and we're going to be comparing the distance between each of these neighbors with that upper bound on the furthest element from W to Q. So only if E is closer to our furthest element in that dynamic list of found nearest neighbors. So, say we entered the graph with 3 entry points from layer 1, and now we're in layer 0, and we're exploring the neighbors of that closest one. If it's not, if the distance isn't less than the third, that third, as I said, the 3 at that highest distance, then we're not going to add it to the queue and so on. So basically what they find is that when you get to the mid phase of the search, say you have 10 of these nodes in your queue now, and you're looking for that 11th as you're exploring, or you're looking to add a 10th and then prune out one of the 10. What they find is that over 80% of these distances you aren't at is lower than the upper bound distances further. I mean, so you're not adding it to the queue, and thus it's not even worth computing the distance, so we approximate the distance. So in conclusion, because most of these distance calculations don't contribute to the search, we can afford to approximate these calculations. So now it's time for the devil in details, I think the most important thing to understand about the paper. So how are we going to be approximating distance? So we're going to be showing how to approximate L2 distance with projected and residual components. So let's start off by just a quick recap of that idea of projected and residual components. So the core intuition is that we have this query vector, and then we have the neighbor of the center node C that we're exploring. We always have this reference where we're looking at 4E neighbors from C. So there's always that kind of relationship as you're exploring nodes. So we're going to be projecting the query and the, my arms don't bend that well, but like to the center node C. So we have the projected and residual components. So basically, I think the key thing to understand is that the projected component is like how much of this vector is this other vector. So it's going to be a scalar times the original vector. So Q sub proj is T times the vector C. So, and similarly D is B times the vector C. So that one is pretty straightforward. And then the residual ends up being the Q minus the projected component is how you then derive the residual. So with the D projections, we can compute all of that offline because we build a big matrix of the of all the edges. So we already know what D projected onto C is going to be, and we already have these edges to compute that with. So let's get into the calculation, and then we'll step through each of the 4 key terms in the equation, and then see how it's computed. So L2 distance, Q minus D, so we're going to break that into the projected and residual components, and then you kind of like multiply that out and you end up with these other terms. So the first thing to note, so if you'll see my mouse, is first we split apart just the basic thing of, Q becomes the projected plus the residual, and then D similarly is the projected times residual, and you multiply that minus sign through it. I don't know how much of the algebra I should walk through when you're separating it out, but so, then you continue separating it. You end up with this term, as you see this again comes like here as you're breaking into the L2 distance between vectors. You often write it as like, A minus B transpose times A minus B, and then you multiply that out and you end up with the, the plus 2 A transpose T, B, sorry with the T again. But so you end up with this term, and because the projected components are orthogonal to the residual components, this term just, exits out. But I think the only thing to be seriously interested in is what you end up with, which is this final thing. So we have these 4 terms that we need to compute. So similarly, if you're approximating the dot product, you don't need to have these additional norms in the final calculation. So you have these just kind of inner products. So, if you're interested in L2 distance versus cosine angular distance, personally, in my experiments with playing with, vector search for a while now, I've never found that, especially with deep learning produced vectors that are already kind of scale normalized for the sake of optimization, I just use L2 distance. Maybe somebody has an opinion about that, and I'd be happy to hear it. But I think let's just stick with L2 distance for now. All right, so as we looked at the derivation of L2 distance into projected and residual components, we're left with these 4 key terms. And this is the key detail to understanding this paper, is understanding how each of these 4 terms are computed offline. Okay, so the first term is going to be the L2 distance between the query projected and then the neighboring node projected onto the center node, the projection components of each of these vectors. So the first insight is that both of these query projected and the neighbor projected are some scalar times the center node C. So we have T times C and we have B times C, where T and B are scalars. So from there, we're going to break the L2 distance. We're going to take out that C that's common to both, and then we just have T minus B squared and then the L2 norm of C. So we pre-compute the norm of each of the nodes. So, for every node in our database, we've computed the norm of it. So we just look this up. This is a part of the extra memory cost that we'll look into later. So then T minus B squared is just a subtraction, multiplication to itself. So it's not like we don't do any computation, but this is, as you see in the top of the memory reads in the arithmetic, is counting how many, the low level of how many additions and so on that we need to compute. So B can also be pre-calculated by looking at the same equation. So, B is going to be that component of the neighboring node D of C in that, and you can compute that offline. So let's get a little more into this. So So this t equals query transpose times c divided by the norm of c. That's going to be like the coefficient. When you project a vector onto another vector, it would just be this then times the c again, I think. Yeah, so from there you can just break down. So then, remember, we already loaded in the norm of c from that we pre-computed. So now we just need to do this top part, the query transpose times c. So that just ends up being the norm of the query, again, the norm of the center node that we already computed. And then we do need to do this L2 distance between the query and the center node. But we only need to do that once to explore the neighborhood of this center node. So in these HNSW graphs, they often would have like 32, 64 edges per node. So we just compute this once to then explore the 64 neighbors of the center node. And to each of these D's as we're looping through the neighbors. So that's how we get the first term, and hopefully it's clear that just the the decomposition into scalars, how we're able to pre-compute the norm, and then how exactly we compute the t by having it's the coefficient of the projection kind of, and then we break the transpose into this. So the next two terms are pretty quick to derive. So with the residual norm, we just compute that offline. We just look it up from memory to add it to our four terms to calculate the the q res transpose d res. So then we have the norm of the residual component of the query. So the way that we do this is, again, the query equals the projected plus the residual components. You've separated the original vector into the residual and projected components, just like plus each other. And so to get the residual component, we'll just subtract the query from the projected component. So the projected component, so again, we calculated that t value in step one. So we're now going to square t and multiply it by that norm of c that we've pre-computed and loaded into memory. And so now we'll just, we just have the projected component that we calculated from t squared times the norm of c, and then we just subtract the query from that. The norm of the query, sorry. And again, the norm of the query is something that we've already computed. So these are scalars as we've computed the norm. Hopefully that's clear. Okay, so now for the most interesting of the four terms, the angular distance between the residual components of the query and the neighboring nodes. So first we're going to break out this transpose dot product into the norm of the query plus the norm of the neighboring node's residual component times the cosine distance between the residual component of the query and the residual component of the neighboring node. So this is where now we're going to look into the singular value decomposition that is used to do this approximation. So what we're going to do is first we're going to create a matrix, this D sub res, the residual matrix, where each entry in the matrix is the difference between the vectors. So if there's an edge from A to B, the first entry in the matrix is going to be A minus B, and so on. Then A to F, the next one is the difference between A to F. So we construct this big matrix that way. And then we get the low rank basis by doing singular value decomposition, where a singular value decomposition, you decompose the matrix into the eigenvectors, and like the top R singular values, they capture most of like the variance in the vector. So it's like, like about project, it's kind of like how TSNE and PCA and like low dimensional algorithms work. It works like that, where you say these are the components that capture like the variance in the data. So the data being the residual matrix, like the distance matrix. Hopefully that's clear. So like that is the top components of that distance that you then use to project the vectors into that space. So okay, so now let's look at how we get the other half of that term, which is going to be the projected residual component of the query. So first, what we're going to do is we're going to leverage that we've already computed a lot of the stuff that we can use to derive this without having to do the multiplication, or having to compute the residual component and so on. So we begin by knowing that the residual component is going to be the query minus the projected component. So we decompose that into q transpose b minus q projected transpose b, and then from there we expand the q transpose projected, again, remember, is t times the center node. That's what the projected vector is, this t times c thing, and t is the scalar of like how much of the center node the projected component of the query is. So then we break that up into, again, the t is calculated like this, where qtc, and again we've already calculated that, so we already have that calculation, and this this QTB, the reason that's interesting to put in the front is because we can just compute this once for the query to then do our entire search with. because none of these are dependent on the center node C. When we're projecting or the residual component, there's always going to be that reference C that we're doing this from, whereas the QTB, that's just universal to every single traversal we're going to do. So then we get the QRes TB from these subtractions, and then we take the sine of it, and then we just have the Hamming distance between the residual transpose B that we derived from this, and then again the dres TB that we've computed offline and saved as this binary representation. Okay, so hopefully that's a clear explanation of where we get each of these four terms from. Then we just combine them by adding them together, and then we have the distance of the query and this neighboring node D. So they show later on when they ablate the comparison between that SVD of the residual and compared to, say, if you don't have these additional terms as well, so you only took the sine of the Hamming distance between the the residual of the query and the residual of the distance. They'll show some ablations on why having all of these terms helps with the stability of this algorithm and the accurate approximation of the distance calculation. So let's get more into the memory cost of doing this, and I think that'll really help clarify what's happening here. So for each node, we're calculating the projection of it onto that low rank basis. So this is what we would then use as reference in those CTB. So this is computed for each node if we're then going to be exploring from that node to its neighbor. So this node is going to be the C in our reference, and then we're exploring the D neighbors of C. So then we also compute the norm of each of these nodes that we again look up several times in the calculation. So this is the extra memory for each node. Now the memory comes for each edge. So we have, for each edge, we're going to have the sign code. So again, we have that dres TB. So we're computing that and storing that offline. So that's our binary representation of the residual projected with the B. Then we have 4 bytes of the projection coefficient B. So again, we use that B to have the T minus B squared in the calculation of the original distance of the projected query and the projected node. And then we also store the norm of the residual component for each of the nodes in the edge. So the residual component with respect to this sourced, so like if it's A to B and we're looking at it from the perspective of B and A is like our C center node, lowercase c. So we're storing the residual of that, the norm of that for each edge that, again, we look up several times with this calculation. Putting that together, that results in the additional memory being the number of nodes we have, the delta V for vertices, graph being made of vertices and edges. We have the number of vertices times 4r plus 1, and then the number of edges times r over 8 plus 8. So what that ends up meaning is, so let's say, for example, we have the data set, the gist 1 million vectors with 960 dimensions per vector, and say we have a maximal 96 edges per node. So we end up having 1 million times, and then the 4 times, say we use 64 as the low rank for that projection. So we keep the top 64 singular values of that projection, and then we add that with the 96 million edges, of which we then have, in this case, 16 additional bytes per each of these edges. So you can see how kind of the relationship between how many vectors you have and how many edges per node you have and how that scales with this. So I guess kind of interestingly, yeah, so you'd have this 96 times 1 million for the edges. So maybe when you're using this, you'd want to have, I guess the more edges you have, the more computation you would save when you're exploring the neighbors of that center node. But then, that would lead to more memory overhead as you have 96 and then, going on into whatever number. But so in the end, we end up having 1.7 gigabytes extra added with this finger index, or the offline values for the finger index. And so with respect to this gist example where it would originally be 3.6 gigabytes for the data points, and so you're talking about like adding like half. So in addition to the memory overhead, there is the time overhead of calculating all those values. They find in their experiments that it has about 10% extra time, so that's really not too bad. If you look further into the detail, they have the derivation of all those memory reads and arithmetics. If you want to look into the distance between just doing full L2 distance and then the series of steps that we looked at with calculating those 4 components. So another clever technique that they use is distribution matching between the real distances between the neighboring node and the center node and the approximated distances. So what this ends up looking like is shown in the green. You have the real distances tend to be Gaussian distributed, whereas once you approximate them with this projection, they end up being a little right skewed. So what you end up doing is you calculate the mean and the variance of the real distances with that residual matrix, and then you also calculate the mean and the variance of the approximated distances, and so then you would normalize this approximated distance score by having t is the approximated distance, not the scalar, the coefficient from the projected thing earlier, but so this approximated distance becomes what it originally was minus the mean of the approximated distances for all of the distances, and then the variance over the mean of the variance, and then plus the new mean. So that's just a way to try to align the distribution and make it more like the real distribution of the distances. So now let's get into the fun part, the results of the experiment. So they're going to be testing this with 6 different data sets and 2 different distance metrics, Euclidean as well as angular distance. So just in case you were worried about that from originally looking at the difference between the L2 distance derivation and say, cosine distance and so on. So they also do test it with the angular distance. So I think the most interesting thing to see is the GIST 960 shows the biggest benefit. Shown in the red is the HNSW-FINGER. What you're looking at is queries per second versus recall. So in the ANN benchmarks evaluation protocol, you look at different hyperparameters where you can get really good recall by trading off speed by, say, increasing that EF and so on. So they loop through the hyperparameters and then put a plot on each of these curves with the recall and then the speed. So you always are going to have that kind of like accuracy versus speed trade-off when configuring approximate nearest neighbor search algorithms. So anyways, I think the interesting thing is that shown in the top right, the higher dimensional vectors gets much better result. That's also consistent with the 784 from the fashion MNIST. But this one is, the most significant probably here as well, looking at, like 1500 versus, 500. So, somewhere like in this particular, measurement of it, it's a pretty massive speed up. But generally they say something like 20 to 50% faster, but these lower dimensional 96, 100, 128, they don't seem to see as much of a benefit from this. So I think it's also just worth mentioning that the text embedding ADA002, they're 1536 dimensional, so it makes sense to think that the finger would look like this with those particular embeddings. So some additional results are the authors comparing HNSW-FINGER with 2 other techniques that I personally haven't looked into, so I can't speak to too much, but they also add some kind of distance approximation on top of the HNSW proximity graph. They also test the importance of using the finger algorithm compared to just say random projection locality sensitive hashing, or say you don't do the full derivation of the terms and you just measure that QRes-T DRes part at the end. So that's what the HNSW SVD thing is. So they do show that you're getting much better recall by using the finger as it is, where you use the the actual distribution of the data to do the low rank approximation compared to just like random projection where you randomly sample vectors to project it into the space, into the lower dimensional space, and ideas like this. So here are some of the reflections I had after reading this paper. Firstly, I think it's very interesting to consider HNSW-FINGER and product quantization. So product quantization is where you compress vectors by, you have this vector and then you'll slide these windows and then you'll cluster each of the windows and then you will represent the window with the centroid ID. So by doing this, say you had like 2 64-bit values and then you've compressed it to like an 8-bit ID too. That's basically the idea. And so product quantization is about saving memory and trying to reduce the memory overhead of HNSW. But also kind of what's interesting about it is you end up using it for disk-based solutions. So like disk ANN is about you load these pre-computed, you load the compressed representations, and this way you get away with not needing to have so much RAM for doing it. And I think HNSW-FINGER could also have a similar kind of application to disk where you don't really need the real vectors anymore for the actual traversal of the vector as we saw. You're just doing the distances between these pre-computed values that don't require the full precision, whatever the original vector was. Rather, you just have these components. So, even though you're adding memory to the thing, if you want to preserve the original vectors, I don't think you need those original vectors for the actual traversal part. So that's just kind of some quick thinking about it. I haven't really put too much thought into that particularly, but I think the next interesting thing is just measuring the online maintenance of this kind of low rank projection in that residual matrix. What happens as you add more data. That's kind of one of the big things that separates vector databases from vector libraries is people continually add data into the index. So how often are we going to need to recompute all these values, because we would need to like reproject it and so on. That's also the problem with product quantization, is you're doing that k-means to cluster those centroid IDs, and then it's like, well, how many of these do we need to load before we have a representative sample? So I think also that kind of distribution shift could be a really powerful lever for that online maintenance, because if you just know the distribution and you see the distribution starts to skew, you can just kind of align it with that normalization trick. And then further, I just think finally this like using the data distribution in these ANN indexes, they already kind of do that with how the edges are constructed, but I think explicitly doing things like compression with the data itself. Thank you so much for watching this paper summary video of HNSW-FINGER. This paper is such an exciting way to speed up approximate nearest neighbor search by pre-computing these values to approximate that distance calculation. There are a lot of details to this paper summary, and I hope that I got a lot of them right. If you find anything wrong, please don't hesitate to leave it in the comments and help my understanding as well as everyone listening, hopefully. So again, thank you so much for watching. If you want to learn more about Weaviate, you can check it out on Weaviate.io, open source on GitHub, Weaviate/Weaviate, and then on Twitter at Weaviate_IO. Also join our community Slack and discuss these ideas around approximate nearest neighbor search. I think it's so exciting to see more research with this, and it's just such an exciting part of Weaviate is how do we compute these vector distances efficiently. So thanks so much for watching.